Carbonic acid, it turns out, has a profound influence on the relationship between fossil fuel burning that produces CO2 into the atmosphere and climate, which is responsive through the trapping of infrared radiation by CO2 to that release of fossil fuel produced CO2. But the ocean, in its ability to uptake CO2 and form carbonic acid, is a tremendous and important element in controlling climate. So let's take a look at how this issue of CO2 in the atmosphere produces carbonic acid in the ocean. And we start this by looking at a simple case, and that is the interaction between nitrogen, N2 gas in the atmosphere, and what happens when that gas interacts with the ocean or any body of water. So we're going to look at the general case where we have water here and we have the atmosphere here, and we're going to explore what happens when N2 in the gas phase goes into solution to form N2 in the aqueous phase. The first step in this is indeed the fact that N2 in the gas phase converts to N2 in the aqueous phase. Now, one interesting aspect of N2 is the bond strength is so strong that this interaction with water forming N2 in the aqueous solution is a physical incorporation of N2 into the water that's intrinsic to the ocean. But there's no chemical reaction. It's a physical insertion of N2 gas into water. So that N2 will dissolve in this water until it reaches a point where the N2 in the aqueous solution starts to produce N2 back into the gas phase. And it's at that point that we come into equilibrium. So we can write those two, N2 aqueous going to N2 in the gas phase, and we write that as an equilibrium. So that is a physical equilibrium, but it's just as valid as a chemical equilibrium, as we'll see. We can write the concentration of N2 in the aqueous phase at equilibrium is given by Henry's law. And Henry's law turns out to be extremely simple. It says that I can calculate that concentration of N2 in the aqueous solution by simply recognizing that it's an equilibrium between the pressure of N2 in the gas phase divided by some constant, and we're going to call that Henry's law constant for N2, and we're going to put a little superscript on it just to keep track, because we have to watch exactly which Henry's law constant this is, because if you look in various pieces of literature, some people use it this way, some people invert it, but we'll just keep track by the superscript of which one we're using. And so now we have a very simple way of calculating the concentration of N2 in that aqueous solution, because Henry's law constant is measured. It's actually done experimentally. So we have those data in tables and we can look them up immediately. So let's turn our attention then to the case in point here, which is how CO2 in the atmosphere interacts with water to produce carbonic acid. So we're going to follow exactly the same approach. That is, the Henry's law constant allows us to immediately calculate the CO2 in the aqueous solution given a particular partial pressure of CO2 in the atmosphere. So let's just write this down. We can calculate CO2 aqueous, and that concentration is equal to the pressure of CO2 in the atmosphere, that is in the gas phase, divided by our Henry's law constant specifically for CO2, and we're going to use the superscript prime here as we did before. But this is where things become interesting, because that CO2 aqueous reacts with water. That's what's so remarkable about carbon dioxide. As it enters either a raindrop or the ocean, that CO2 in the aqueous phase, controlled by the Henry's law constant, reacts with water to form H2CO3 in the aqueous form. That's carbonic acid. And we've already seen that carbonic acid is polyprotic. It's got two hydrogens, but it also comes into equilibrium. And of course, immediately as we see that an equilibrium is set up, we're very curious to know what the Gibbs free energy release looks like for that chemical reaction. And in fact, we can write this, the solubility of carbon dioxide forming carbonic acid, as an equilibrium. That is H2CO3 aqueous divided by concentration of CO2 aqueous. And notice that that's the aqueous concentration of CO2, not the gas phase. And of course, we can write water into this expression, but we know that it's pure water, so it has an activity of 1, so we don't need to write it down. That's the equilibrium constant.